Okay, we're going to talk about quadratic models, okay? Now, in this question, we actually already know this is a quadratic, which if you're plotting like models of like maybe coordinates or something like that, sometimes you have to like estimate what would be best. And usually, something like this is a curve of best fit, which kind of fits a parabola, which is quadratic. So we assume we've already gone over that information, okay? And we've discovered that there are two x-intercepts. Those are the points when you cross the x-axis, which is this axis here, right? At -2 and -6. So we know it's crossing there. So maybe we discovered that, it did something like this, the model, and they cross at this point. So we decided it's quadratic, those are the x-intercepts, and one of the coordinates that's along the curve of best fit is at -3 and 6. Okay, so here's one of the coordinates in it. What we want to find out is like maybe an optimal value, what the vertex of this quadratic would be, a whole bunch of information like that. Okay, so in order to do that, we're going to work with the factored form, and the factored form deals with the x-intercepts of a quadratic. Okay, the factored form of a quadratic is written as y is equal to a, which is kind of what decides how long and thin the parabola is going to be, that variable. It's called stretching and compression. X minus r. Okay, r stands for one of the x-intercepts, and x minus s. Okay, so in our case, our two x-intercepts happen to be -2 and -6. So we're going to plug them in for r and s. Okay, so we can plug those numbers directly in. We get y is equal to a, x, and technically it's subtract -2, okay, and x subtract -6. Okay, does that make sense there? Okay, which means this is going to read y equals a x plus 2, x plus 6. Okay, so when in this factor form we have our two brackets, these are kind of counterintuitive. They're opposite of what the actual x-intercepts look like. Okay. The only other variable we don't know is this a, but we do know a coordinate, and this coordinate here, which is our -3, 6, is actually really important. That is a y and an x value. So here's my x, here's my y. I can replace the y in the equation with 6, and I can replace the x's, or the x in the equations, right, with -3. So let's kind of go about doing that. So our y will become 6, which will help us isolate for a. Our x becomes, what number do we say? -3, right? So -3 plus 2, and -3 plus 6. Okay. So from there we get 6 is equal to a, -3 plus 2 is -1. And -3 plus 6 is 3. Okay, we'll multiply those together. 6 is equal to a times -3. And how do I isolate and get a by itself?
Divide by -3.
Yeah, we divide by -3. So what is that going to give us?
Sorry, -2.
Yeah, that's right. -2. So our a value is -2. So if we were to actually write a model for the equation, okay, we take the information we had here where we had the values, and the only thing we're missing is a, and we'll plug it in. So now we get y is equal to, remember our a value is now -2, so -2 times x, and then technically it's plus 2, that's the simplified version, and then x plus 6. Okay, I'm just going to rewrite it in black so it looks, oh, that's wrong color. I'm going to rewrite it in black so it kind of looks like a final answer there. But that's it. We've drawn out the regression model, which is really good because this factor form gives us a lot of info. From this factor form, what we can find, okay, we've got a model, an equation, but we still kind of missing some stuff because in a parabola there's some kind of peak. And in this case, it's -2, right? Because this is a negative function, that means it's opening downwards. Had it been positive, it would be opening upwards, doing something like that. And because it's negative and going downwards, that means it has a max. This is considered the maximum of the function. It's also known as the vertex. If it was opening upwards, this is still the vertex, but it's called the minimum. It has a lowest point, okay? So we want to find that max in our case, or in other words, the vertex. And one of the ways you do that is you find the middle point between -6 and -2. So just intuitively looking at that, where do you think the middle of -6 and -2 is?
-4.
Yeah, this makes sense, right? That would be kind of the middle. And this middle is called the axis of symmetry. Now, algebraically, the way we solve that, okay, so we call it our AOS, axis of symmetry. Algebraically, what we do is we add our two x-intercepts together. And remember, they're way up here at -2 and -6, and we divide by 2. So I'm going to give you the formula saying x1 plus x2, because those are x-intercepts divided by 2. In our case, that's -2 plus -6 over 2. Okay. -2 and -6 is -8 over 2, which gives us -4, which is exactly what you had solved. So this is a symmetrical line. We know that the parabola has a vertex or a maximum at that point. Okay, this is where if we were to flip it, it would look identical on both sides, but we just don't know where it crosses that point. It could be way up there. Okay, the axis of symmetry will be the x value of the vertex. So if I was told to write the vertex of this equation, the axis of symmetry, which is at -4, is the x value. Okay, we know that's where the x is going to lie. Our question from here is, where's the y? Okay, well, we can figure that out very simply. We take that -4 and we plug it in to this equation. That's why we needed to have this equation. So we're going to plug it into that idea. Okay, so I'll take that equation, y equals -2, and our x value in this case is -4. Okay, plus 2. And what's usually neat when you're in this factor form, it's not always true, but it is common, what'll happen when you plug the axis of symmetry in, okay, to the factor form, or a proper factor form, it should happen very. What you're going to get when you deal with the brackets, you get -2 and +2. Essentially, you get the same value, one's a positive, one's a negative. And that should very commonly happen in our factor form. Okay. So from there, I have -2 times -2 times +2. I'm going to go through this quickly. Negative times negative, so positive, which means we now have a positive times positive, which is a positive. 2 times 2 is 4. 4 times 2 is 8. So y equals 8. So our top value is at 8. Okay, that's the y value of the vertex. So now if we were to draw a rough sketch, we know we go from the vertex, ooh, that was kind of ugly, to that point there. And we know we cross this point because we were already told that. So we cross that point and come through this x-axis. So now here's my rough sketch. Because it's facing down, this is a maximum. They also call this like the optimal value. This is essentially the highest it will go. If it was going the other way, the minimum would be considered the optimal value. Okay? And finally, the last thing I want to talk about is a Y-intercept. Okay? Now, looking at the graph, it might be really hard to figure out where this Y-intercept is. It might fall off the chart. But one thing we know about our Y-intercept, it's when the x value is 0. So again, because we have our equation, we can find it really easily. Instead of plugging in -4 where the vertex was, this is where x is 0. So we're going to plug 0 in for those x's, okay? So I'll take that same equation, y equals -2, and I'm going to plug 0 in for the x. Okay. And now we're going to solve for the y value again. This becomes -2 times 2 times 6, okay? 2 times 6 is 12, times 2 is 24, and it's a negative, so -24. So it makes sense that it really doesn't show up on our graph, right? It's going to be way down there at -24. But that's important to us. Y-intercepts are sometimes very helpful when we're looking at models and stuff like that. Okay, essentially that idea is once you have the equation, I can plug in any x value. So I plugged in -5, and it would tell me what my y value is. If I plugged in 4, it would give me some y value super low down there. It doesn't even really show up on our chart.